In this video, we will discuss about the Laplace transform by using the property 4, which is the Laplace transform of a derivative and also the integral. We will cover this in this study, where you can see that if you perform the Laplace transform of the first derivative, you see that you multiply the s with the fx, and then you have to minus with the initial condition. And when you take the second derivative, then you have to multiply with x squared x power of 0, and then you have to minus with the initial condition f0 and initial condition f prime 0. On the other hand, if you integrate your time function, then in the Laplace domain, it has to be divided by x. As you can see, when you take the derivative on the left hand side, so f power of n is equal to this, where if you have a first order, you have f prime, okay, then you have a df over dn only. If you have second order, you have double prime or 2 here, it means d square f dt square. So n means the order here. And if you take the integration for your time function, then in the Laplace domain, you have to divide by x. So we also call this as the multiplication by s property and also division by s property. Let's say you have ft, and if you perform the Laplace transform, you obtain the fx. If let's say you differentiate the f with respect to t, so this is the first derivative. So on your Laplace domain, you need to multiply with s, and you need to minus with f0. So what is f0? So this term is ft when your t is equal to 0. So you substitute your t equal to 0 inside, it will be your f0. So be careful, bear in your mind the f0 here indicates ft when your t is equal to 0. So if you have second derivative of the f, then you have x squared minus x minus x0. So x0 is 1. So you have capital Fx. So small letter f0 initial condition. So this is initial condition also, which is f prime 0. For the third derivative, you have the x power of 3, power of 2, power of 1, power of 0, which is 1. And then you have capital Fx, and then initial condition f0, initial condition f prime 0, and there's a double prime f0, so please correct this. So this is the general formula where you have n derivative, then you start from s power of n, s power of n minus 1, s power of n minus 2 until s power of 0, which is 1. Then you have capital Fx, you start from f0, f prime 0, f double prime 0 until the n minus 1, 0. This is very useful in solving ODE problem, so please remember this. This is the Laplace transform definition. So when we want to perform the Laplace transform of a derivative, so we can just substitute the derivative function inside this definition. By using the integration by part, let u to be the exponential term here, and the rest to be equal to dv. And you find the du and v on this, substitute inside the formula for uv minus v du. So substitute the limit for infinity inside, you get exponential negative infinity. So in this case, you get 0. Substitute the 0 inside, exponential term here, you get 1, and you get f0 here. So you get 0 minus f0, and you can simplify into this. On the right hand side here, since you integrate with respect to t, then in this case, your s will be the constant. So we can take out the constant negative x outside. So negative x outside, you get positive x here. This term is fx, so we get s fx minus with fu. So this is our answer. With that, we can prove that Laplace transform for our df over dt gives us this answer, which is same with the previous answer here. Let's try to solve the following ODE equation with initial condition. So you have initial condition f0 equal to 5, f prime 0 equal to 2 here. And this is your ODE. First, we perform the Laplace transform on the both sides. Then by using the linearity property, you can separate the term into this. Initially, it is in time domain, and after you perform the Laplace transform, you convert it into S domain. So let's start with the Laplace transform for the ft function. Then you should get capital Fs. So if you take the first derivative, df over dt, then you should have s minus 1, then capital Fx minus with the f0. So the initial condition based on here, you know that is equal to 5, therefore you can substitute 5 inside. So we continue with the next term. So you have a second derivative here. So second derivative, you start with x squared. So x squared minus x minus 1. Then you have the capital Fx minus with the initial condition minus with the f prime initial condition. So substitute the f0 equal to 5, and then f prime 0 equal to 2 inside here. So with that you obtain this equation. On the right hand side, you have Laplace transform for sine tan t. So sine tan t, you know that is s squared plus omega squared, where your omega is tan. So therefore we put tan squared inside. And the formula at the top, it should be a constant. So you have omega at the top, which is equal to 10. Then you have 9 here, so you need to multiply 9 with this Laplace transform result. Therefore, in total, you get 90 over s squared plus 10 squared. We arrange the term for the fx. So we have 3 terms here to be equal to this. And then the rest, you have constant, negative 2, constant plus 25. Therefore, you get 23. And you have remaining negative 5x here, which is this. Negative 5x plus 23, you move to the right hand side, you get this. And then this one, you move to the right hand side, you divide. Then you success to find the fx equal to this. But from the ODE, what we want is we want to find the ft. So you have to perform the inverse Laplace transform to find it. With that, we can find the ft equal to inverse Laplace transform for the fx. So we substitute the fx here. So you should perform the partial fraction technique to get this, where you have the quadratic factor and linear factor here. And for this term, you have linear factor. After perform the partial fraction, you get the decomposition to be this. For the first term, you have a constant multiplied with x over x squared plus 10 squared. So x squared plus 10 squared indicate is a cos or sine function. And at the top is a s, so it will be the cos tan t. So you multiply the 225 over 5668 constant multiplied with the cos tan t, you should be able to get this Laplace transform result. In the second term, you have 10 over x squared plus 10 squared. So this is sine tan t, and you multiply with the corresponding constant. So you have x minus 3 here, where your a is equal to 3. So therefore you substitute the exponential at, where your a is 3 here. And this one, your constant a is 2, so your exponential is 2t. So with that, you obtain the ft answer. In this example, we have the same ODE as the previous example. However, it's given boundary condition instead of the initial condition. So to solve this problem, again, we perform Laplace transform on both sides. And using the linearity property, you can separate into 3 parts. Then you perform the Laplace transform for the second derivative. And you found that for the f0, you can substitute equal to 5 here. But for f prime 0, we don't have such information. This is the limitation for the Laplace transform, where we cannot perform the Laplace transform to solve the ODE equation with boundary condition. So we cannot solve this by using Laplace transform. Laplace transform is a very powerful tool that can solve the multiple ODE problems simultaneously. So for example, in this case, you see there are two ODE equations. So when you have more than one ODE equation, this is called as system of ODE. This equation represents multi-degree of freedom mass spring system. So you have one mass and two mass here, where your mass 1 is equal to 1, mass 2 is equal to 2. And your spring K1, K2, K3, assume the positive x to be this direction. And let's say you hold the thing, okay, for the mass 1 to be -1 from its equilibrium position. So you pull the thing by x0 equal to -1. And on the other hand, you pull the block to +2 from the equilibrium position. So 2 is equal to x0 in this case. The response at mass 1, we can represent it to be x10, which is equal to -1. So 0 here means that at time equal to 0, you hold the thing in this position x equal to -1. At the same time, on the right hand side, you have the mass 2, and the response due to mass 2 is given by x2. So at time equal to 0, you hold the thing at +2. This is the initial condition for S1 and S2. S1 prime and S2 prime is equal to 0, indicating the initial velocity is 0, which means you do not give any impact to the mass 1, mass 2 at time equal to 0. What you want to predict is when you release the block here, you want to know what is the vibration of the block 1, which is the x1t over the time, and also what is the vibration for x2 over the time. So these are the two solutions that you are looking for. In this example, we have two ODE, ODE1 and ODE2. So we will start to solve the ODE1 by applying the Laplace transform on both sides. And when you perform Laplace transform for the second derivative, you obtain x squared minus x minus 1, and then since this is the derivative for the x1, then you have capital x1x minus with the initial condition x10 and the initial condition x prime 10. On the right hand side, Laplace transform for the x2. So x2 is in time domain. After you perform Laplace transform, you get the x2x. And Laplace transform for the x1t is equal to capital X1x. Then you collect the term for the x1. So you have the first term and second term here. So we move this term to the left hand side, you obtain x squared plus 3. And then you collect the term for the x2 here. So you move x2 to the left hand side, then you obtain -2x2x. So you have the remaining term on the right hand side, which is the x10 plus x prime 10. Then you can substitute the initial condition. So x prime 10 is equal to 0, this can be cancelled, and x10 is -1. So therefore you obtain -x. By moving the x2 term into the right side and then divide with the x squared plus 3, then you can obtain the x1x. We perform the same procedure for the ODE2 as well. So we perform Laplace transform on both sides, and then for the first term you have the second derivative of it. Once you perform the Laplace transform, you obtain x squared minus x minus 1, and since this is x2, you have the capital x2x, x20 and x prime 20. Then on the right hand side, x2 term here become x2x, so x1 term here become x1x. Then you can substitute the initial condition inside. So x2 0, this term is 0, can cancel, and then x20 here is 2. So once you substitute here, it becomes -2x. We collect the term for the x1. So with x1, we move to the left hand side, you obtain negative 2x1x. Then we collect the term for the x2. So this is the x2 term, and this is the x2 term as well. So you have 2x squared plus 4. This is the answer. And lastly, you have the negative 2x multiplied with the 2 here. So you get negative 4. When you move to the right hand side, you obtain 4x. To find the x1 and x2x, you can substitute the equation 1 into 2 to find the x2 here. Once you find the x2, then you can substitute back into the first equation to find the x1. By doing that, you should be able to obtain the x1 to be this. However, this procedure to find the x1 and x2 is very long, so I do not recommend you to use the substitution to find it. Imagine that we have more than 2 ODE, let's say 3 ODE and above. So in this case, by using the substitution method, it is not recommended because it takes a longer computation time. Please use the matrix method to find the x1, x2 in this study. These are the previous two equations where you have x1 and x2 unknown to be solved. We can rearrange this equation by using the matrix, and you get a matrix format like this, where you can check it, take the x squared plus 3 multiplied with x1, then minus 2 multiply x2, you get equal to negative 2, which is equation 1, and take the negative 2 multiply x1 plus 2x squared plus 4 multiply x2, you will get equal to 4x. So these are the two equations in matrix format. Then you can apply the Cramer rule to find the x1 by using this equation. So this is the determinant for this matrix, and the matrix at the top here, so determinant here you can see you need to replace negative x 4x to here. To find the x2, you need to replace the negative x 4x over right side. So this is the formula to find the x1 and x2, and you should be able to get the answer similar like previous one. Please take note that to factorizing the polynomial which has the order more than power of 3 and above, you should use some calculator. To find the factor, in this case, you have two quadratic factors from this polynomial which has the order equal to 4. We can use calculator where you can check by let it to be equal to 0, you get the root to be 4 number. First number is I, second is negative I, third is 2i, and you have negative 2i. With that, you can form it to be 4 linear factor like this. And we don't form linear factor with complex number. So you have to multiply the pair of the complex conjugate. So let's say you take the x plus I multiply with x minus I, you will get x squared plus 1, and then you take x plus 2i multiply x minus 2i, then you get x squared plus 4. So this is how we get this factor. You have succeeded to obtain your x1x, so this is the answer. Our aim here is to find xt by using the inverse Laplace transform. But if we look at this format, it will be quite complex, so we simplify it by using the partial fraction decomposition. So you have quadratic factor x squared plus 4. At the top you must have the linear factor ax plus b, and the a and b are unknown. So similarly, you need to find the c and d unknown here. So these are the procedure that you have learned in engineering mathematics 1. So you should be able to get a, b, c, d to be this answer. So your a is equal to negative 2, b and d is equal to 0, and c will be equal to 1. So after you substitute, you get this. Then we take the inverse Laplace transform for the x1x. So we take the inverse Laplace transform for this term. You get x over x squared plus 4. If you take the inversion, then you get cos 2t. because you have x squared plus omega squared. Your omega squared equal to 4. So therefore, your omega is equal to 2 here. So why is cos? Because at the top you have x. Right? So x over x squared plus 1. So your omega squared is 1 in this case. So your omega is 1. Therefore, you have cos t. Don't forget multiply your negative 2 constant here. So you success to obtain the first answer for x1. This is the answer in Laplace domain for the x2. You have to perform the partial fraction. So this answer can be equal to more simple form like this, where you have quadratic factor here, and you need to find the unknown a, b, c, d. So by performing the partial fraction, then you obtain the a to be 1. Okay, this one is 1. And your b, d is 0. So this one is cancelled off. And then your c is 1 in this case as well. With that, you obtain this answer. And then s over x squared plus 1. If you convert to time domain by using the equation of Laplace transform, then this is equal to cos t. And since you have 4, omega squared equal to 4 here, so you have cos 2t here. So this is the final answer that you obtain from the ODE, where you have x1t and x2t equal to this. So what does this mean? To know the meaning for this equation, so you can plot it. So this is the equation from x1t, which represent the vibration, movement, left and right for the first mass, and x2 is the vibration movement, left and right for the mass 2. So you can see that the vibration is quite complicated and complex. And based on the initial condition that you have previously, so you know that at time equal to 0, so time equal to 0 is at this point, time equal to 0. So you displace the x1 to be negative 1. So you see the initial position for the block mass 1 is here. And your x2, the initial position is 2. So your mass 2 initial position will be here. So 2. So you see over the time, let's say at time equal to 10 here. So your mass 1 will be at this point. At time equal to 10 here, so your mass 2 will be here. At time equal to 18, your mass will be at this position for mass 1, and your mass 2 will be at this position, this one. So you see the vibration between these two masses. And you success to predict the vibration movement from the initial condition in this case. In this property, if you perform the Laplace transform on an integral, then in the Laplace domain, your fx should be divided by the x. This is the proof for this property. So if you take the Laplace transform for the integral, so the integral will be our function in the definition. So let us have u to be the integral and dv to be the exponential dt. So when we take the integration for the dv, we get v, and integration for exponential negative xt, you get this. And if we take the differentiation for this, we get back the ft. So we can apply the integration by part, which is the uv minus v du. Substitute the limit infinity inside this, you get exponential negative infinity, which is equal to 0. And then you substitute the limit 0 inside, you get 1 over negative x, which is this term. And then 0 substitute to t here, you get integration from the 0 to 0. So the area for this is 0 as well. So in this part, okay, you can get 0. So on your right hand side, so negative x here can be extracted out. So you have 1 over x here. So negative become positive. And when we look at this term, is the definition for Laplace transform, which is fx. So this is your final result, which is our property. There's typo here, please correct this. So you should read Laplace transform for the integration equal to this. In this example, we have integral equation like this, where your C, R, E constant are given, and your initial condition at t equal to 0, your current I is equal to 0. So we have to find the current versus time, where we don't know what is the IT here. So after you substitute all the constants, you get this equation. And for the first step, we apply the Laplace transform on both sides. So for this term, you get the Laplace transform for the integration for IT. So you know that from the property, when you perform Laplace transform for the integral, it should be equal to fx divided by s. So with that, in this case, you integrate the I, therefore you have ix divided by x. Laplace transform for the IT here, you get capital IS. 20 is a constant after you perform Laplace transform, then you get 20 over s. Then we can collect the term for ix. Move this term to the right hand side, and then you get this. Then to remove the x, you multiply x at top and bottom, so you get this. And to remove the 160, you divide at the bottom 160 and at the top 160, then you get the final form here. So from here, this is in Laplace domain. We have to perform the inverse Laplace transform to get your IT. So in this case, 0.125 is a constant, we can take it out. So you have inverse Laplace transform for 1 over x plus 62.5. So in this case, based on the formula x minus a, you know that your a is equal to negative 62.5. With that, we can find the time domain to be exponential at, where your a is equal to negative 62.5.